Alright, so today I'm going to talk about conventional 12-tone tuning systems. So, in music, everybody knows we have the chromatic scale, which goes from C, C sharp, D, D sharp, all the way back to C. But there are a lot of ways that we can actually define these pitches, and there are a lot of ways throughout history in which they've been defined. So, I'm going to do a brief review on the Overtone series real quick, since this will lead us into just intonation really well. So, the Overtone series is basically the natural series of notes that happens if we take a string. Let's say we vibrate the string so it bends up and down like this. Let's say this would give us a C, like a C2 maybe. If we then divided the string in half, so it vibrated like this, we would get twice the frequency, which would give us a C3. And we can continue this pattern. So I have to keep erasing and whatnot to make room. If we broke it into 3 sections, we would get 3 times the frequency of our original C2. We would get a G3. And we could continue doing this forever. So just intonation is based around the idea of the Overtone series as being pure and natural. So in just intonation, we like to think about ratios. So let's say we want to build the just intonation C major scale. So let's start with our lowest C. So just for ease, I'm gonna refer to each of these notes with their ratios. So if you're unfamiliar with ratios, definitely rewatch my first lecture that I did on overtones and stuff like that. But basically, when I write a ratio, that has to do with the ratio of its hertz to the hertz of this base C. So since C is in unison, it has a ratio of 1-to-1 with itself. Kind of duh. So we can also define the C that's above it. I'll call this C prime, would be 1 octave above, so we're going to say it has a ratio of 2-to-1. Because again, with the Overtone series, if this is a C, maybe C2, then twice that, double the frequency would give us C3, an octave above. So doubling the frequency gives you the octave. So we have our octaves. Now let's do the fifth. So if you remember, if our base was C2, then our overtone series would go like this. We would have G3 would be the third overtone. So if we had a G that was 1 octave above, we would have a 3-to-1 ratio, but we want to lower it an octave. So we're going to multiply that 3-to-1 ratio by an octave down, so times 1-to-2, and this will give us G of having a ratio of 3-to-2. So again, that means that G, the frequency of G, and the frequency of C have a 3-to-2 ratio. Now we can also do a fifth down. So if G is 3-to-2, then in F, why don't I just use numbers? So let's just say this is C2 again. This is C3, this would be G2. If we had F1 below that C2, it would be 2-to-3, right? Since F1 is a fifth below C2. We would just be inverting the ratio for a fifth. But we want to bring that up an octave, so we're going to multiply it by 2. So we have F2 is 4-to-3. Now, if we follow the overtone series a little bit farther, we get that E4 is the fifth overtone. So E4 would be 5-to-1. And if we lower this by 2 octaves, we would get E2 is not 5-to-1, but 5-to-4. I'm going to rewrite those 2's. They're kind of bad. All right. So now we have a couple really nice intervals we can start to work with. So let's try to construct what's it called? D. So D2 is going to be, think of it like this. We're going up by a fifth, gives us G, and then down by a fourth, gives us D. So D2 is going to be 3 to 2, which is a fifth up, times 3 to 4, which would be a fourth down. Does that make sense? Since the ratio for a fourth would be 4 to 3, so going a fourth down would be 3 to 4. So if we multiply those, I'll go with the ratio, ruler. If we multiply those, we get 9 to 8. And then we can do similar methods of multiplying intervals to get that A, which would be basically up a fourth and then up a third, a major third, would be 5 to 3. And we would get that B2 would be up basically a fifth and then up a major third, and that gives us 15 to 8. So now we have really nice just intonation ratios for all the notes in our C major scale. However, not everything is as nice as it appears. So before I discuss some issues, I want to define what the unit of a cent is. So a cent is a really common unit that you see when you talk about tuning or frequency or that sort of thing. Basically, the way we define a cent is that imagine we have the interval between C3 and C2, right? So we have all the possible frequencies between those. We define the interval of an octave to be 1200 cents. In other words, what that means is one half step, so maybe that between C2 and C sharp 2 in equal temperament would be 100 cents. So whenever I talk about cents, that's what it means. 1 cent is a 100th of a semitone. So that's going to be important a lot. So the main issue that we have with just intonation is a phenomenon known as comma pumping. So I'll show you what it is. So let's say that we wanted to have the following progression, and I'm going to clear these intervals. Let's say that we had the following sequence of notes. We went C to G to D to A to E, and then back down to C. Okay? So we had this series of notes. Let's see what happens if we construct it using just intervals. So up a fifth, and I'm going to write these as fractions, the same thing. Up a fifth is 3 over 2, times down a fourth is 3 over 4, times up another fifth, 3 over 2, times down another fourth, 3 over 4, and then finally times down a major third. Now what does this equal? So we can cancel out these 4s. And ultimately, if we multiply the numerators, we get 81, and the denominator, we get 80. That's not good. That means that the ratio of this C, so I'll draw this C in blue, the ratio between blue C and red C is not 1-to-1. In other words, those C's are not the same note. Those C's are off by this very small ratio right here, 81 to 80, which is called the syntonic comma. So this isn't good. So where does the syntonic comma come from? So the issue comes from this assumption here. We assumed that, I'll do in green, right here, this interval from D to A, we assumed that it was a perfect fifth, 3 to 2. However, if we examine our ratios a little bit more carefully, so I'm going to clear this real quick. Let's examine our ratios again. We said that D had a ratio of 9 to 8 with C, and we said that A had a ratio of 5 to 3 with C. So in other words, the ratio between D to A, so I'll say the ratio between, or I'll do A to D, my bad. The ratio between A and D would thus be 5/3 times 8 over 9, or in other words, 40 over 27. Now, if we put this into our calculator, you would notice right away that this is not the same as 3 over 2, right? This is not 3 over 2, so this is not a perfect fifth. In fact, it's flat by about 20 cents, so it's flat by 20 cents. This is definitely audible. If you listen to this interval, it's going to sound definitely flat enough to be jarring. You'll notice that something is out of tune here. And oftentimes, these sorts of fifths that are just slightly off are called Wolfe Fifths. And I'm going to talk more about Wolfe Fifths as we go on. So don't worry about that too much right now. But so we see that just intonation fails ultimately as a tuning system because of these inconsistencies. We either say that yes, our interval is in fact the pure one, so we would say yes, we want it to be 3 over 2, but if we do that, then we're going to drift off of our original pitch. We will no longer have the same C. Or we have to say, no, our intervals are out of tune and sound bad, but we won't drift pitch. So these are kind of the failings with just intonation. So let me check chat to see if there are any questions. Are there any questions yet? Okay, I assume not. So how are we going to deal with fixing just intonation? Because just intonation, in theory, in that C major scale we constructed, sounds very nice. Those pure simple ratios sound very harmonious, and in fact were used in most of early Western music. So let's jump back a little bit in time and talk about different forms of just intonation. So before we even had that specific system of ratios that I showed you, we had something a little bit simpler, which is called Pythagorean tuning. Pythagorean tuning basically posited that all tuning should be based around the fifth. So Pythagorean tuning. So what Pythagoras would say is that, okay, 1 to 1 would be 3 to 2 again. D, we would construct in the same manner by stacking fifths and get 9 to 8. Now we go up to A, which he would argue we need to stack another fifth to go. So we're just going to basically keep multiplying 3 over 2 by itself. So we would get 27 to 16. Then we would have E, which at this point is starting to get ridiculous, is 81 to 64. And right away, you should notice something. Our syntonic comma, or I'm sorry, this is not a syntonic comma anymore, but we have a comma. Because normally, our old just intonation E, if you recall, was 5 to 4, which is the same thing as 80 to 64. So, in fact, I'm sorry, this is a syntonic comma, because these two E's are not equal, right? So the E that we want, that pure interval, is going to be off from the Pythagorean E by 1 syntonic comma. And so Pythagorean tuning actually has really awful sounding thirds, and generally the farther you drift away along the circle of fifths, the more wildly out of tune your intervals will go. So Pythagorean tuning fell out of fashion with the advent of modern Western music, but it was very common in Greek music where thirds were considered dissonances anyway. So in the modern formulation of tuning systems, we would call this three-limit tuning. And the reason we call this three-limit tuning is because all of our intervals are only using factors of 3 and 2, right? So all of these numbers here on the left side are only using 3 and 2. No other primes. There are no 5s, no 7s, no 11s, because we're only stacking fifths. Now, in the modern day, we want to have things like 5 to 4 for our major third, so we don't use three-limit tuning. In just intonation, we would typically have what's called 5-limit tuning. The 5-limit starts with the assumptions that C, or the octave C is that. We have G, the fifth, is 3 to 2. And we also now include the assumption that E is 5 to 4. And you can again think of this like the overtone series, which goes like this, right? So now instead of cutting off our overtone series here, as Pythagoras would do, we cut it off here. And think about how we construct all notes using those first notes of the overtone series. And furthermore, we can go on from that, and we could say include 7-limit tuning, which would also include the harmonic seventh. So B flat in quotation marks would be the interval 7 to 4. So this would be including now these notes of the harmonic series. So we would stop there, and that would be called 7-limit tuning. And you can have basically any prime number as your limit for tuning. Generally, the higher your number for your limit, the more possible sounds are going to be available to you, which is, in my opinion, a good thing. But usually once you get beyond 7-limit, it becomes kind of meaningless to even think of things as ratios. So there's not very much musical theory that goes into, say, 11-limit tuning or 13-limit tuning. It just starts to lose meaning. So those are the different kinds of just intonation. I think it's good to know what those words mean. But just intonation is not commonly used, so what do we use instead of just intonation? So one possible solution to these commas would to be, let's say we had a keyboard, but instead of just having, our vertical, nice friendly keyboard, worst keyboard I ever drew, what if we had a two-dimensional keyboard? So in other words, we had maybe our normal keyboard like this, and then we stacked another keyboard on top of it that was up by 1 syntonic comma. So this is +1 comma, and then we had another one which would be +2 commas. And such a keyboard probably exists somewhere, but obviously making that sort of tone space, thinking about music in terms of a two-dimensional tone space, not a good idea. So, and besides, the weird theorists, that sort of thinking is generally rejected, and that's kind of why we reject just intonation in general. So another way to try to solve this problem is to temper out the comma. So instead of having this awkward comma, we want the comma to go away a little bit, and we're going to spread out that unevenness across pitches. So this is where we include this idea of mean tone tuning. So mean tone, let me pause for a second to see if there are any questions before I get ahead of myself. By awful sounding thirds, do you mean too flat or too sharp? It's going to be too sharp by exactly one syntonic comma. It'll be one syntonic comma sharp. 20 cents sharp. Any other questions? Okay. Oh, I totally forgot. I'm sorry. Pause on meantone. I forgot one last thing I wanted to mention about Pythagorean tuning. Pythagorean tuning also creates a bit of an issue because think about it like this. If we start at C, here's C, and we were to keep stacking, major fifths, we would eventually get to, we would go G, D, A, etc. And eventually we should wrap back around and we would get F, B flat, F, and then C again, right? And the hope would be that this interval right here between the F, which is 11 stacked fifths, and our original C, so this is the same C as back here. I should really specify. These two C's are going to be the same. We want this interval to be a perfect fifth, right? However, it's not. It's actually called, this is the Wolfe Fifth in its most common usage. And the reason it's called the Wolfe Fifth is because it is extremely flat. It's flat by 23 cents, which is called the Pythagorean comma. So Pythagorean comma. And because it is so obnoxiously flat, it has been said to howl like a wolf. So that's kind of the silly origin of that name. But yeah, that was the last thing I wanted to mention, is that's the Pythagorean comma. If you ever see that, that's what it means. Difference between this Wolfe fifth that we get from Pythagorean tuning and the perfect fifth. Okay, I think that is definitely all I need to talk about just intonation. F and C flat is the Wolfe fifth? Yes. Itch. If by C flat you mean like a flat C, then yes, because the F that we get by stacking 11 perfect fifths is going to be a little bit too sharp. So the Wolfe fifth is going to be a very slightly flat perfect fifth. Okay, so let's talk about mean tone. So, like I said earlier, Pythagorean tuning really ruins the third, and just intonation is just too inconsistent to really be viable for people that are not singers and cannot deal with microtones, which is pretty much every instrument. So we invent mean tone tuning. So mean tone tuning was, let me write it. Mean tone tuning was invented in 1523. Yeah, 1523. I have notes, I promise. By this dude called Pietro Aron. Fairly slick guy. He decided that fifths or thirds should sound really nice, and they don't if you just use Pythagorean tuning. So why don't we distribute the syntonic comma, so that our fifth is in tune? Because if you remember, in Pythagorean tuning, we said that E, the major third, was off by a syntonic comma. So the syntonic comma, from here on out, I'm going to just write SC because it makes my life easier to do. So I'll talk about a couple common mean tones. So there are three common systems of mean tone tuning. You have third, in order of commonality, I'll say, you have third comma mean tone, quarter comma. So I guess I can't really say fourth. People will hurt me. Quarter comma. And equal temperament. So let's talk about third comma first, since it's the least common of the three common systems. So the idea behind the third comma meantone is that you want the E flat, in other words, the minor third, to be perfectly in tune. We want it to be a perfect ratio of 6:5, which would be its just intonation ratio. And so how we're going to do this is we're going to lower the perfect fifth. We're going to lower the fifth by 1/3 of a syntonic comma. So we're going to lower G by 1/3 of an SC. So I'm just using G because C major is easy to talk about. So what would happen if we did this? So if we stacked fifths, sorry, we don't want my bad, it's not E flat that we want to be 6:5. It's going to be actually the A to C is going to be 6:5, C to A. So we want basically the minor third that you get from A to C to be in tune, not C to G, E flat. So how does lowering the G by 1/3 of a syntonic comma help us? So let's construct A. So if we start with C and we move along the circle of fifths, G, D, A, we would be getting 3:2 times, well, this one would be technically 4:3 since we'd be going down a fourth, and then we want to go down actually another fourth here, right? So if we multiply these across, we would get 3 cancels out here, this turns into a 2, cancels there, we get 8/3, and then adjusting, ooh, that shouldn't be right. What did I do wrong? What the hell? Hold on. Oh, I know what I did wrong. Sorry. C, G, D, A. So we have 3/2, 3/4, because it would be a fourth down. And then here we would have another 3/4 going down a fourth, would give us 27 over, that would be 32. So in other words, flipping that would be 32 over 27 would be the minor fifth that we get, right? But we don't want this to happen. So we're lowering the G by 1/3 of a syntonic comma, which would actually make our new intervals, instead of being the ratio 3/2, we're actually going to have the ratio be 3 to the 1/3 power, or in other words, the cube root of 3, I believe. So going up by this 3 times, no, my notes have to be wrong here. This is not going to work. Okay, I'm sorry. My notes are wacky here. I didn't really do my best research on third tone, mean tone. But just take my word that this is slightly too sharp, I believe. And so lowering the G by 1/3 of a syntonic comma should bring this down to the desired ratio of 6:5. Okay. Trust me on that. I don't really want to talk about this system much because it really isn't important. Not that many people use it. The really important system is quarter comma mean tone. So quarter comma mean tone seeks to make the major third as in tune as possible. So we want E, C to E. Sorry, I keep doing this backwards. E to C we want that to be a 5-to-4 ratio. So what we're going to do is we're going to temper the, what's it called, the major, or the perfect fifth by 1/4 of a syntonic comma. So G is going to be lowered by 1/4 SC. And if you recall what I said earlier, in Pythagorean tuning, E to C would be 81 over 64 when we want it to be 80 over 64. So now, if we go along the circle of fifths, basically stacking fifths like you would do in Pythagorean tuning, we get 81 over 64. However, if we use our new lowered G, then we're going to be adding 1/4 of a syntonic comma, or I'm sorry, removing 1/4 of a syntonic comma at each step. So by the end, adding all those up, we're basically going to be lowering our result by 1 syntonic comma, which gives us the desired 80 to 64 ratio, which is the same thing as 5-to-4. So that's the idea of quarter tone mean tone, is we're going to be reducing the fifth, making it slightly flat in order to preserve the third and other intervals. So I want to give you a good visualization that is on Wikipedia for this. So I'm going to have to adjust my window settings. Let me look for questions. Dang, everybody left. Oh well. Third comma wants the thirds to be in tune as much as possible. It wants the minor thirds to be in tune as much as possible. But of course, the minor third is not as important as the major third overall. So you usually want to use quarter tone mean tone. Yeah, that's kind of the idea. And it doesn't tune up every minor third. I want to keep that clear. It's specifically tuning up the minor third that goes A to C, basically. All of these mean tone tunings still have the same issue with pitch drift if you do a full migration around the circle of fifths. So let me pull up this visualization real quick. I'm going to have to change my window settings so you guys can see it. Mean tone. I'm just stealing it from Wikipedia. It looks cool. How do I switch? Screen. Change windows. Okay. So you guys see this picture right here? So this picture basically gives you, in black, is equal temperament. And each of these lines represents how far each note drifts off from equal temperament as you stack fifths. So as you can see, Pythagorean tuning goes a little sharp. Like I said, ultimately, if you were to go around, that last fifth, F to C, is not going to be a perfect fifth. It's going to be slightly lower than a perfect fifth, which means that Pythagorean tuning actually overshoots. So that's why it has a positive slope here, is if you stack 12 fifths in a row, your resultant C is going to be above a typical C by a Pythagorean comma. Now, if we look at quarter comma and third comma mean tones, they actually undershoot in order to preserve the fourths and the purity of the fourths. So if we did a full octave, we would actually undershoot the C. So I think that's a good way to think about the failings of different mean tone systems. You can kind of think of Pythagorean tuning as a mean tone system. Instead of being quarter comma or third comma, it's just no comma, because it just lets the syntonic comma act normal. You also notice on this visual that I think is important is you see these lines here. It says syntonic comma. That shows the difference, how different a syntonic comma really is. And then also you have the Pythagorean comma over here at the end, which shows you how basically wrapping around the Pythagorean comma, wrapping around the Pythagorean tuning, going from G sharp to A flat, lowers you by a Pythagorean comma. So anyway, just cool visualization. Let me switch back real quick, and I can talk about equal temperament, which is the friendliest of all the systems. Whiteboard. Okay. So, basically, equal temperament, or ET, can be thought of as the same thing as, what's it called? Basically 1/12 comma. So what we're doing here is we're going to lower the fifth by 1/12 of a comma. So now G to C, or C to G, is going to be basically our ratio, but minus 1/12 of a comma. So think about G to C, G to D. Each of these are removing a 12th. So if we go all the way back to the beginning to C, we will have removed one syntonic comma, which is exactly what we want to remove the issues of Pythagorean tuning. We need to get rid of the syntonic comma so that we go back to C. So equal temperament is really great because it is the only system, at least in terms of mean tone and other common systems, where there is no pitch drift. It is impossible to have any commas because each semitone is the same distance apart. So the distance between C and C sharp is just going to be 2 to the 1/12. This distance between F sharp and G is just 2 to the 1/12 to 1. I should be clear. So the spacing between every semitone is equal, which is really great because we don't have pitch drift. However, there are a lot of issues with this system being out of tune. I got a ping, so maybe that's a question. Oh, you guys can't see? Oh, snap. Hold on. Thank you. That's bizarre. I wonder why you guys couldn't see. Tell me if you see it now. Yeah or no? Anybody? Can you see?
No.
Dang. Why is this happening to me? Okay, we're just gonna do this. Go live. Can you see it now? Anybody? Yes, okay, good. Okay. So, sorry that you guys couldn't see that, but equal temperament, 12th comma, the distance between C and C sharp or any other semitone is going to be 2 to the 12th power, which is, in other words, the same thing as the 12th root of 2 to 1. And so this means that all of our semitones are going to be really nicely, evenly spaced apart, which is great. We don't have any pitch drift, and each key sounds exactly the same. However, the issue with this is our intervals are not going to be very pure. Notice, first of all, that the perfect fifth is going to be off by 1/12 of the syntonic comma. That's just the definition of this system. Our thirds are also going to be out of tune. So if we look at C to E, this ratio exactly would be would be 2 to the, sorry, quick maths. This would be 2 to the 1/3 to 1. So why don't I just stick that in a calculator and see how much that is. Okay, so this is going to be sharp by a decent amount. So this is basically 1.26 to 1 when we would want 1.25 to 1. So our major third is going to be sharp, right? And all of our intervals are going to be somewhat off from what we really want them to be. So that's kind of the main issue with equal temperament, is it sounds kind of ugly. So we want some way to marry the idea of no pitch drift with some of the purer sounds that you get from mean tone playing. So I'm going to actually try to share a video that I found yesterday of a mean tone organ so that you guys can hear what I mean by the purity of a mean tone sound. So this was the video I found yesterday. Tell me if you can hear it. Hopefully you can. So I'm just going to skip a little ways in. Skip. Don't look at my YouTube recommended.
Now, you might notice me with perfect pitch may notice that doesn't sound like C major, because in reality it's almost a half step sharp.
Let me back up a little bit.
And down front. For example, in the key of C major, this instrument excels in so many ways.
Okay, thank you. Caspar, can you hear it? Hold up. Can somebody else let me know if you can hear it or not? Dang. Let me switch my screen. I think that might be the issue. Change windows. Go live. Okay, how about now? Can you see or hear it?
Now, you might notice me with perfect pitch may notice that doesn't sound like C major, because in reality it's almost a half step sharp. The instrument in Germany after which this is designed was tuned.
What? Are you serious? Hold on. I'm terribly sorry for technical difficulties. I don't want to restart Discord because I am recording. Perhaps I'll stop the recording here and maybe that will help. I mean, I said pretty much the main part of the lecture. So I'll stop the recording here and then try to continue streaming on Discord.